talk about randomized algorithms. We call an algorithm randomized if its behavior is determined not only by its input, but also by values produced by a random number generator. Okay, and there are two categories for randomized algorithms. One is Las Vegas, another is Monte Carlo. The Las Vegas category, for any input, the algorithm always produces the same correct output. The running time of the algorithm depends on the output of a random number generator. In this course, the algorithms we're going to discuss are all from this category, Las Vegas. The other category, Monte Carlo, for any input, the output can be different depending on the output of a random number generator. Okay. Randomized algorithms are often more simple and have better asymptotic bounds, with only a small probability of being slow or wrong. Okay. We focus on the first category, Las Vegas, and we're going to see two examples why we use randomized algorithms and what problems we can solve by using these randomized algorithms. So first of all, let's go back to the hire problem once again. We made the analysis for the expected number of hires based on an assumption, and the assumption is all the applicants come in random order. So what happens if we do not know the distribution of the input? Because we do know there are certain applicant orders can trigger the worst case of the hire assistant algorithm. And if an agency likes to send applicants in that order, then we cannot rely on our previous analysis on the expected number of hires, right? We have a quick fix for that problem. So before we hire any assistant, we perform this line 1, randomly permute the list of candidates. So we do not assume the candidates come in random order. We permute them. We permute them randomly. And then the algorithm is the same as before. It is easy to see the expected hiring cost of the procedure is also C sub h line n. However, there is a difference. So in the analysis, we have to calculate the expected value of an indicator random variable y sub I, and this is the indicator random variable for the event the candidate I is hired. And in both analysis, we have this value equals 1 over I. And for this randomized hire assistant procedure, this is true because of line 1. And in our previous analysis, this is true because of the distribution of the input. So that's the difference. Okay. So compare hire assistant and randomized hire assistant. The expectation for the randomized hire assistant is for any input. Okay. And it's not for inputs drawn from a particular distribution, and that's a very different situation here. And in both cases, we got the same expected cost. And hire assistant is deterministic, meaning for any input, the number of hires is fixed. For example, I have 3 input sequences we have seen before, and for each one of them, the number of hires is fixed. The expectation is over different inputs. And for the randomized hire assistant, it's not deterministic, meaning, for example, for input A sub 3, the number of hires depends on the outcome of its permutation. Could be 1, could be 10, we don't know. We can only say the expected number of hires is line m. So this expectation is over different executions. So that's the difference between hire assistant, and randomized hire assistant. Now let's discuss some design points for randomized algorithms. And once again, we focus on Las Vegas category, which means for any input, the algorithm always produces the same correct answer. The running time of the algorithm depends on the output of a random number generator. We design this type of randomized algorithms by introducing some randomization operations. We do this when we don't know the input distribution or we want to avoid some worst cases. And then we need to use probabilistic analysis to verify or to establish the efficiency of our randomized algorithm to see whether we achieve our goal.